Hello everyone. In this video, we're going to take a look at a few more examples from Chapter 9. My name is Fred Rispoli, and I'm coming to you from Stony Brook University. So in particular, we're going to look at two examples involving proportions and one example involving variances. And you may recall Chapter 9 is all about inferences concerning two samples. So on our roadmap for hypothesis testing, we're over here on the right side to sample. We're going to look at proportions and variances. You can see that we're still assuming the underlying distributions are normal distributions. So a few formulas for proportion inferences. The one you see here is a formula for our confidence interval for the difference of two proportions, P1 minus P2. P1 hat, so that's the sample proportion for the first sample. P2 hat, sample proportion for the second sample. The z alpha over 2, that's our term we get from a normal distribution. M is the sample size of the first sample. N is the sample size of the second sample. And we can calculate these sample proportions. They're fairly easy. P1 hat would be the number of successes in the first sample divided by M. And similarly, P2 hat, number of successes in the second sample divided by N. Another term we need to be familiar with is this test statistic Z. So Z, you can see we have P1 hat minus P2 hat. And in the denominator, you may notice this is just a P hat. This is sometimes called the common proportion, P hat, which is simply the sum of x plus y over the sum of m plus n. So it's like a pooled proportion. You see that term here, and we have this times 1 over m plus 1 over n. All of this underneath the square root sign. So we'll take a look at all of these in the next two examples. They'll come up. So in our first example, this is about confidence intervals for a proportion difference. So suppose we're given that incidence rates from asthma from samples obtained from smokers and non-smokers are given below. You could see that with smokers, there was a sample of size 993, and there were 209 people found with asthma. And for non-smokers, the sample size is 1,012. 172 were found with asthma. In Part A here, we're asked to find a 95% confidence interval for the difference in asthma incidence rates between smokers and non-smokers. So here our incidence rate is our proportion. And then in Part B, we're asked, does the confidence interval suggest that the asthma incidence rate is different between smokers and non-smokers at the level of alpha is equal to 0.05? So this is a question that we could do using hypothesis testing, but you could think of this in terms of we're going to come up with the solution to the hypothesis test using the confidence interval we obtained in Part A. All right, so here's the calculations for the confidence interval. We find P1 hat 209 over 993. So this gives us a proportion of 0.21 or 21%. P2 hat, you could see we get 17%. So it does seem like they are in fact different. The P1 proportion does seem higher. We'll eventually see, is this significantly higher? We'll be able to answer that. But first, let's put together the confidence interval. So we have a formula that looks like this. This first expression here is the difference in the proportions. So I have 0.21 minus 0.17. We calculated those up here. Then the error term has this z term, z of 0.025. Right? Remember, alpha is 0.05, but with the confidence interval, we divide alpha over 2. So this leaves 0.025 in the two tails. This is a value we've seen over and over again in chapter 8 and 9. We get 1.96. I believe I have that here. So again, we're thinking 0.025 in the right tail, leaves 0.975 to the left. The z value we get is 1.96. So we have that term over here. And then underneath the square root sign, we have P1 hat, 0.21, times 1 minus P1 hat, 0.079 over 993, plus the fraction 0.17 times 0.83 over 1,012. So you may want to stop the video. Always a good idea to practice these calculations. Here we'd have to sort of simplify the two fractions first, then add, then take the square root. Once we have that, multiply by 1.96. And so this term here should simplify to 0.034. So we start with this difference here is 0.04, and we have minus 0.034. So you can see that's going to give us 0.006 as a lower bound, and then 0.04 plus 0.034 gives us 0.074. Okay, so this is the confidence interval for the difference in the proportions. So now to answer question B, once again, question B says, does the confidence interval suggest there's a significant difference in the asthma rates? So if you were setting up the hypothesis test here, we'd have something like P1 hat is equal to P2 hats. If we think of that in terms of differences, it would be P1 hat minus P2 hat is equal to 0. Okay, so the key to answering this is to see if 0 is included in the confidence interval. Right, remember the null hypothesis would be P1 hat minus P2 hat is equal to 0. The alternative would be either P1 hat minus P2 is not equal to 0 or is greater than 0. If you wanted to think in terms of, well, you know, the smoker incidence rate is greater than the non-smoker rate. Okay. So we can examine this confidence interval and observe that 0 is not in the confidence interval. And from that, we could conclude that the difference is significant at this alpha equals 0.05 level. So sometimes we could use confidence intervals to carry out a hypothesis test. For the most part, it can be done when you're looking at a two-tailed test. In that case, the confidence interval really becomes the acceptance region. And then on the two outside tails, that would be the rejection region. On to example 2. So here we are going to run a hypothesis test for two proportions. Suppose we know a certain refrigerator manufacturer claims that the fraction P1 of his refrigerators that need repairs in the first 10 years is less than the fraction P2 of another brand. To test the claim, the researchers observed 150 refrigerators from each brand, found that 20, this is in the first sample, needed repairs, and 36 in the second sample need repairs. Does the data support the manufacturer's claim? Conduct a test using alpha equals 0.05. All right, so we're going to use our 5-step method. First step, set up the hypotheses. So the null would be that the two proportions are equal. The alternative is that his brand, okay, the person making the claim, their brand is less than the other brand in terms of the proportion that need repairs. So we could label H1 the claim. Alpha is given to be 0.05. Our test statistic, here's the formula we looked at a few slides ago. So we need to calculate a few things before we substitute into the formula. We need to find P1 hat. So that's X over M, 20 over 150, or that is the decimal 0.133. P2 hat is 36 over 150, simplifies to 0.24. And here's the pooled proportion, the P hat, X plus Y over M plus N. So we add up 20 and 36. So this would give us 56 over 300, or 0.187. And our rejection region here, so we have to think in terms of a left-tailed test, right? We get that from the alternative hypothesis. This tells us a left-tailed test. The rejection region would be a z-value less than minus 1.645. So we get this number from our normal distribution table. We're interested in the value that leaves either 0.05 to the left. So if we were to look this up, we look for 0.05. How close can we get to 0.05? We see that 0.05 is exactly the midpoint between these two values. So the value that's used would be this minus 1.65 would bring us right here. So that's where the minus 1.65 comes from. Step 4, we work out the calculations by substituting into the formula. Some people may call this a z-test. So in this z-test, we have 0.133, right? That's the P1 hat, minus 0.24, that's the P2 hat, over the pooled proportion, 0.187 times 1 minus 0.187, which is 0.813. And then we have this term here, 1 over m plus 1 over n, 1 over 150 plus 1 over 150. So we figure out these two fractions, add them, and then multiply these, then take the square root, do the subtraction in the numerator. So this should work out to minus 2.377. Compare that to the critical value, we see it's less. So that would put this in the critical region. And the statistical conclusion would be to reject the null hypothesis. So we're going to reject this hypothesis. So we can say that the data supports this claim. And here a p-value is straightforward. It's a one-tailed test, so I don't need to multiply by 2 or anything like that. We get the p-value is the probability Z is less than minus 2.38. So we could just confirm that over here. We look up minus 2.3. Here's where we get this 8. So minus 2.38. You could see we would get 0.0087. And that is, in fact, the p-value. We just confirm this is less than 0.05. So the p-value is low. The null must go. So that just confirms we did the right thing here. Reject the null hypothesis. So that concludes example 2. Next, let's turn our attention towards variances. We have just 2 formulas here. We're really not going to do much with this confidence interval. I did want to go through an example, though, where we have to look at this F statistic and compare to see if we have equal variances. That's a very important type of test. You may remember when we were running t-tests for 2 samples, we had one case where we assumed equal variances and a second case where we looked at unequal variances. So this test would also be done before we run a 2-sample t-test to see which of those 2 cases are appropriate. So this becomes important for a couple of reasons. All right, let's take a look at the example. Suppose in a statistics course, one group of students had access to a set of videos online in addition to the class notes, and the other group of students did not have access to the videos. In each case, an exam was given after the lectures, and then we're given a score. So we're assuming both cases or both courses are taught in the regular way, but one group of students has an additional resource, online videos, and the other does not. So let's say that we have these 2 samples. These are the scores for the group classroom and videos, and this is classroom without the videos. We want to test to see if the variances of the scores are different between the 2 groups. I'm going to use alpha is 0.05. So the first thing you have to do here is calculate the variances, right? This is one of those problems where we have the raw data. So we need to find the sample 1 variance, 341.3, the sample 2 variance, 22.3. Null hypothesis is that the population variances are equal. The alternative is not equal. So when we're running a test for variances to see if 2 variances are equal, we use the F statistic, which is just the ratio, the sample 1 variance over the sample 2 variance. Now the rejection region has 2 critical values. Okay, the first is if the F calculation is greater than this, and notice there's 2 degrees of freedom. Okay, the sample sizes were both 5 and 5, so here our degrees of freedom are 4 and 4, and we need alpha over 2. So we need the value from an F distribution table corresponding to 0.025, 4, and 4. So let's take a look at that. All right, so here's a table that I put in the lecture notes. This table doesn't go up very high in terms of degrees of freedom, but it has the different alpha values all on one table. Okay. You have to pay careful attention when you're working with the F distribution, because some tables are just based for one specific alpha. You get a higher degrees of freedom on both sides, but just one alpha. Others are set up like this, where we have 3 different levels for alpha. Okay, so here our alpha over 2 gives us 0.025. We have 4 degrees of freedom for the denominator, 4 degrees of freedom for the numerator. So our value would be right here, this 9.60. So this would be the value here, or the critical value. So the thinking is when we run our test, we'll get a value for capital F. If it's greater than 9.60, then we would reject the null hypothesis. But there's also the left tail. And when we have the symmetry here, in the sense the degrees of freedom is the same for the numerator and the denominator, the 4, 4, the other critical value is just 1 over the one we used up here. So here we would have 1 over 9.60 gives us 0.104. So now we have our 2 critical values. We calculate the F statistic. It's 15.31, and that's, you can see, much higher than this critical value here. So we're sort of out there in the right tail of this F distribution in the critical region. So here's a case where we would reject the null hypothesis. So we're rejecting over here. So we could conclude that there's enough evidence that alpha equals 0.05 to demonstrate that the variances are different. So if there was a 2-sample t-test for the means, this would tell us that we would need to use the case where the variances are not equal. Okay, and this concludes the video, and it's also the last video for the course. So good luck with the rest of the course.